For all of you that keep a journal or a diary, this is an historical moment for you. This is the moment in which we start to take derivatives in calculus. You'll probably want to probably blog about it or something. Anyway, so let's take a look at what our objectives are. We want to be able to find the slope of a tangent line using a limit definition. All right, and then find the instantaneous velocity of an object in rectilinear motion. Rectilinear motion is this kind, or just goes back and forth on a line. And finally, find the derivative of a function at a point using, once again, the limit definition. All right, so let's start with our traditional warm-up question, and it's one that we've kind of seen before. What is a tangent line? Well, remember, it's not quite as simple as just saying it is a line that touches a graph at just a single point, because you can see here, this tangent line touches at both A and someplace over here on this sine graph, right? So I'll pull that Desmos sketch out again, and then I can move this tangent line wherever I want it. And remember, that local linearity aspect of it, that if I were to zoom in and zoom in, the tangent line and the graph start to mimic each other. They start to land on top of each other, meaning that the tangent line and the graph at that point have the exact same slope. They're going to be going in the same direction. That's how we stated it the first time that we looked at this, way back when in chapter 2 here. What's a tangent line? Well, tangent line is a line that hits a curve at just a single point over some sort of interval, right? So yeah, it hits down here. This pink one over here, T, is tangent to this curve C. It hits it twice, but we only care right here at P over an interval that contains that particular point, and it has to go in the same direction. And I can kind of think of slope as that direction, meaning that the blue line here definitely not tangent to this curve. If we were to really, really zoom in at that point, it would look more like the pink line, not the blue one. All right, which brings us to our first objective, being able to find the slope of that tangent line using a limit definition. We finally learned how to take limits. I think that we're pretty good at it now, right? And we're going to apply it to the problem. You remember the tangent line problem? Exactly, right. That's what we're going to apply it to. Since we cannot find the slope of a tangent line directly, remember you only have one point. Sure, it might hit someplace else down on the graph someplace, but you have no idea where that's going to hit. So we can't find it directly. We have to find it indirectly with a secant line. And so we looked at this basically the very first lesson, finding the slope of this secant line. I'm going to pick another point. I'm going to go to the right by some h value. Maybe it's like a half. Maybe it's even smaller than that, 0.1, something like that. Gonna just so that I can get another ordered pair on our particular function here. And now I'm just going to find the slope between those two things, right? All right, so I'll find the slope. It's the slope of a secant line. I think I can handle this. So our slope should be equal to, I know it's a change in y over a change in x, okay. And then our change in y here are these two y values. So f of a plus h, right? And then minus f of a all over. And now I need to do the change in x's here. So a plus h minus a, and then our a's cancel, right? Same exact difference quotient. That's what we called it back there in that first lesson of calculus. And now, hey, this isn't really what I want. This is the slope of a secant line. And I need to get that h as small as possible, right? That's going to be accomplished with a limit. As h approaches 0, then the slope of this secant line is going to start approaching the slope of the tangent line. So I'll pull up Desmos again, and we had a sketch for this one as well. Tangent line problem. It's right here. Collapse that thing. So right now I have my secant line through point P and point Q right there. And if I wanted to make the tangent line or try to get closer and closer to the tangent line, I'm going to shrink down my h value. H value is just this orange segment down here on the x-axis. It is the change in x. It's how much I have to, say, move to the right in order to get a second point to actually find the slope, right? So I'm going to try to make this thing as small as possible, and I can accomplish that with a limit, which brings us to, finally, the actual definition of a tangent line. So the one we looked at the beginning of the year and at the beginning of this lesson, it was pretty informal. So here is the actual definition of a tangent line to the graph of y equals f of x at the point P at a comma f of a is a line through the point P with slope, watch this, m is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. So again, this is the slope of the secant line, and we're trying to make this h as close as possible with the limit. Of course, it can't be 0. If we plug 0 in here, we get f of a minus f of a, that's 0 over 0. I get that indeterminate form, and what I'll have to do is all the techniques that we learned in the previous lesson or the previous unit on how to resolve that 0 over 0 thing, provided the limit exists. All right, so here's another little tidbit. Of course, as we mentioned, the slope of the tangent line is also the slope of the graph at that particular point, right? And we saw that with the local linearity. If we really zoom in on that particular point, it starts to look just like the graph, has the exact same slope, right? And here's another picture for it. One more thing, the h value that's in here, this is one way that we usually see this with just this h, but h is the same thing as how much I change by x. It's the same thing as delta x. So sometimes we see the exact same definition, or we see these limit problems written as the limit as delta x goes to 0 of f of a plus delta x minus f of a over delta x. Well, if you think of slope, it's change in y, delta y over delta x. It's the same thing. It's just that this top part here is obviously dependent upon the delta x, and so it stays as f of a plus delta x minus f of a. And we just keep this delta x down here in the bottom. I wanted to show you that because we're going to sprinkle this throughout the lesson just to keep things fresh. And also in the AP Calculus exam, you might see it in terms of delta x, and I don't want it to freak you out the first time you see it.